Welcome back. We're on our final question, question 3 of 3 of our free response practice here for forces. By now you probably know the drill, right? Do the practice first. Then after you do the practice, watch the video. So I'll assume you're ready to go. We're told that we have these two blocks of mass m and 2m connected by a light string and placed on a frictionless inclined plane that makes an angle theta with the horizontal, as shown above. Connected to a light string to mass other m, to a hanging sphere of mass m that goes over a pulley of negligible mass and negligible friction. The entire system is initially at rest and in equilibrium. Right, so remember that there are all of these important things that they are giving you, and so you really need to take time to work through and break down. Excuse me for a moment. Let's close these. You really need to take time to think through the problem and break down what are all of the key things that we've been given. There's a lot of important information to be found in this opening statement. Right? First, we're told it's in equilibrium. So that means that our net force is 0. Which isn't told by initially at rest, right? Be careful. Initially at rest doesn't mean that it won't necessarily accelerate when things are maybe let go, right? We're then told that all of these things, light string means that we don't worry about the mass, light string, pulley with negligible mass and negligible friction. So none of this is involving rotation. This is all about just Newton's laws. And so now for question A, we are then asked to draw that point mass free body diagram for each of these things here. So we want a point mass free body diagram for this M on the block and the hanging mass M. Each one, remember, must start on the dot and point away from the dot. So careful to not use the engineering free body diagrams. And notice that there's no grid. So we talked about when you see a grid, they really want to look at how are you drawing the magnitudes and are they done properly to follow Newton's laws. But when you don't see a grid, that's not what they're looking for. So I will have the gravitational force capital mg down, and since things are equilibrium, I have this ft, they're giving us 2. So you could write ft2 or just t2 going up. Remember we talked about I don't like t because that's period of oscillation and we can get confused later. So the action is here, the reaction is here, parallel to the plane of the ramp, ft2. We have the weight, which is a lowercase mg, and we have the normal force of, I'll call it normal force 2. And then we're told that the plane is frictionless, so there's no force of friction, but I do also need to have a tension force down that is Ft1 or T1 to represent the fact that there's this other rope here. All right, let's go ahead and look at the scoring for this. So the scoring has 3 points for the free body diagrams for correctly drawing and labeling vectors representing the normal force and the gravitational force on block M. So is the normal force perpendicular to the surface and mg straight down? That's a point. For correctly drawing and labeling vectors representing the forces of tension on block M. So remember drawing and labeling. So do you have T1 parallel to the plane down? Do you have T2 parallel to the plane up? And for correctly drawing and labeling vectors representing the tension force and the gravitational force on the sphere of mass capital M. So did you do this one correctly? That's your third point. Note that you lose a point if you draw extraneous vectors. So if you, for example, put friction on this block lowercase m, you would lose a point. All right, let's continue. So on the next side, we were asked to derive the expressions for the magnitude of each of the following. If you need to draw anything other than what you've shown in part A to assist your solution, use the space below. Do not add anything to the figure. So what this is saying is don't add any components to your original free body diagram, right? So be careful about that. So the first thing that we are asked to do is to show the force T2 exerted on the block of mass lowercase m by the string. Express your answers in terms of lowercase m, theta, and physical constants as appropriate. And then the next one is to find the mass capital M for which the system can remain in equilibrium. Express your answers in terms of lowercase m, theta, and physical constants as appropriate. So the big challenge of this is that when they say derive, that means that there's a lot that they're going to look for. They talk about derive these equations. Generally, these follow a logical order. So you do 1 in order to help you with 2. You do 1 in order to help you with 2. So over to the right here, I'll do the sum of the forces on capital M, just so we see what we're going to need, right? And this is only in the y. And it equals that Ft2 up minus capital Mg. And it equals 0 newtons because A, we're told, is 0. Okay, so what that means is that this capital Ft2 equals the capital Mg. But notice we are supposed to express our answer in terms of the lowercase m. So this would not be our answer. What this shows us is when we're asked what is the mass capital M needed, is that eventually when we come over here we're going to need to substitute for Ft2. And that's where we have to come to the other block. So for the other block, the sum of the forces in the y, or remember what we talked about is that y is the parallel to the ramp direction, is going to equal the normal force minus lowercase mg cosine theta. And things are balanced because the acceleration equals 0. The sum of the forces in the x, which remember we said is the parallel direction, equals well, I guess we should define for this ramp, positive x is up the ramp, just like positive y was up perpendicular to the ramp. We have Ft2 pulling up the ramp. In our diagram, we had Ft1 going down the ramp. And then we also have the sine of the weight of that going down, which all equals 0 for the same reason. All right, so Ft2 is here, so let's go ahead and solve for that. Ft2 equals Ft1 plus mg sine theta. But the problem is that I don't know Ft1. So you can either do our method we did before where you make the two objects part of one system, or if you do the other objects separately, then for that block of mass 2m, we would have to have the gravitational force of 2mg, the normal force on this, and then the tension force Ft1 going up. Right, so the sum of the forces parallel for this one is Ft1 minus 2 mg sine theta equals 0 newtons because same reason. So then we'd say, okay, Ft1 equals 2 mg sine theta. And now we need to substitute up here. So Ft2 equals 2 mg sine theta plus 1 mg sine theta, right, which is then just simply 3 mg sine theta. And that would be our answer for I. Now that we know what Now that we know what Ft2 is, to do double I, it's very straightforward. We would substitute and say that 3 mg sine theta equals big mg. So in order for this to be true, notice that the g's divide out. M must be equal to 3 little m sine of theta. All right, let's go ahead and look at the rubric here to see how this is scored. So part I has 2 points for using an attempt at a correct statement of Newton's second law for the two blocks. So this is where you do the making both blocks the one system thing. So if you do that method, you can just write the net force equals 0 because A is 0, right? And so T2 is supporting the weight of M plus 2M times G sine theta equals 0 for correct answer with supporting work. So I find that as the AP program has evolved, they leave things more open-ended because there's so many different ways that problems can be solved. Basically, if you tried to set up a force equation, you get a point, even if it's wrong. To get the second point, it must be right. Final point for double I, the mass capital M for which the system can remain in equilibrium, we need to express a correct statement of Newton's second law for the whole system to derive an expression for M. So saying, okay, the weight of big M pulling on one side must balance the weight times sine theta of the two blocks on the other side, and then solving. So notice if you use our method of defining your system in very useful ways, it's much easier to set this up. Otherwise, you have to do what I did, which is all this derivation work. So what I would always suggest you do is just identify what is your system. Like I could say that my system for single I is M plus 2M. And that way I could say the sum of the forces, which is 0 because A equals 0, is going to equal Ft2 up minus M plus 2M times G sine theta. Right? And that's a lot faster than what I had to do the other method. So this is where knowing how to identify your system is really valuable. Okay, C. Now suppose that mass M is large enough to descend and that the sphere reaches the floor before the blocks reach the pulley. Answer the following for the moment immediately after the sphere reaches the floor. Does the tension T1 increase, decrease to a non-zero value, decrease to 0, or stay the same? So the first thing we want to think about is this tension T1 that we drew, right? Remember, tension T1 is what is between these. Does that tension T1 increase, decrease, or remain the same? The second one is the velocity of the block of mass M up the ramp, down the ramp, or 0? And is the acceleration of the block mass M up the ramp, down the ramp, or 0? So the fact that they don't ask you to explain means that the points are purely for the check marks. So again, if you're short on time, look for these things and just try to do them quickly. Don't ever leave them blank. So, first point. What happens to the tension? For correctly stating that the magnitude of T1 drops to 0. Let's think about why. For both of these blocks, their acceleration, as soon as this upward piece ends, their acceleration will become G sine theta. So if these both are accelerating at the same rate, then this block down here isn't going to act on this block up here. And this block up here isn't resisting anything that's going on here. They're slowing down and then speeding up together. So the only thing on these now would be the M, whichever M, G sine theta, is the velocity up, down, or 0. So remember that the hanging mass, we're told, hits the ground before these hit the pulleys, so these have inertia. They are going to continue in their direction, but acted on this unbalanced force will eventually slow them down. So they're still moving up, but they are slowing down. And so when things slow down, you have opposite signs to acceleration and velocity, so the third point is for checking down the ramp. All right, so that's how we answer those three checks. Now it says, consider the initial setup in figure 1. Now suppose the surface of the incline is rough and the coefficient of static friction between the blocks and the inclined plane is μs. Derive an expression for the minimum possible value of m that will keep the blocks from moving down the incline, expressed in terms of blah, blah, blah. All right, so part of the reason why I thought that this out of our three practice was probably the hardest is just because I think it's so time consuming. There's just so many steps here that we have to work through to answer all of these questions. I really think it's a long question, given the fact that we only have 15 minutes. So we derived all these equations before, and unfortunately they're helpful but not fully helpful, because now I have a friction force that will be assisting in holding this in place here, and a friction force that will be assisting in holding in place there. Now the easiest thing to do, just like before, is to make all of this our system. All right, so the sum of the forces on our system, which is the three objects, again equals 0 because A equals 0. So we have 0 newtons then equals, and on the one side I have the capital mg still, right? That has not changed. And on the other side I have what I had before, which is the 3m times the g sine theta. But what has made things really complicated is the fact that we also have a minus mu s Fn for one block and a minus mu s Fn for the second block. So one of the things that we'd want to say is that because A equals 0, Fn minus mg cosine theta equals 0. So Fn equals mg cosine theta. Then we have to substitute. All right, so now our equation is big Mg minus 3mg sine theta. And then the mu s is common to both of these, so minus mu s times, so this here is going to be 2 mg cosine theta. This here is 1 mg cosine theta, so this would be 3 mg cosine theta, all equals 0. So common factor of g can go away. I need to move m to the other side, or the other piece is the other side. And now m equals 3m sine theta plus 3m mu s cosine theta. And that's our extra piece there. So that is worth 3 points, but man, this problem is just long. You can see that just because this video takes longer than the others. So it says here, for an attempt at a correct statement of Newton's second law for the system. So even if it's wrong, if you tried to write what the sum of the forces is, you get a point. For an attempt to substitute in for the friction force. So again, attempting. It does not mean that things have to be right when you're grading yourself here. Notice that you get points for showing your work and trying. Always show your work. So if you take what you wrote for the Newton's second law and you replace Fn with what Fn would equal. Maybe you just wrote the wrong thing, but you started here. You have to start with the original and then show the substitution. You get the second point. The third point is then for having the correct answer. Now, the thing that has me puzzled is that clearly I made a mistake in my signs, right? They have sine theta minus mu s cosine theta. So it is a helpful. Usually I keep mistakes that I make in the videos to show how, like, I've been teaching physics for years. Mistakes still happen. All right, let's talk about the mistake that I made. The mistake that I made is that I didn't read carefully. Right? It says that will keep the blocks from moving down the incline. All right. Down the incline means that I had my direction wrong. I was thinking that would keep them from moving in the way we were told before. So I would have lost a point because I set up everything correctly except for the fact I assumed friction would be down, when in reality friction needs to be up to keep them from moving down the incline, which means that I should have made this here positive, which would have made, whenever I rewrote this positive down here, and then this should have been negative. All right, so I would have lost a point there for my solution. Hope that wasn't too disconcerting earlier when you were like, but I had a different answer. The string connecting block M and the sphere of mass M then breaks, and the blocks begin to move from rest down the incline. The lower block starts a distance d from the bottom of the incline as shown in figure 1. The coefficient of kinetic friction is mu k. Derive an expression for the speed of the blocks when the lower block reaches the bottom of the incline. Express your answer in terms of all of these things. So again, this problem is endless. Right? When you run into a problem that's endless like here, my suggestion for you is to set up the things that you would need to solve to try and get those points and then move on. Right? So if we look here, it's worth 3 points, right? 3 points for a lot of work. So for example, what I would do is set up, okay, excuse me, what is the equation that I need in order to, I guess, for kinematics to start? What is the equation that I need in order to find that v? And then what is the a that I need? So if you're looking at the clock and going, I've already spent probably 14 minutes on this problem or whatever, right now in my discussion I'm at much more than that, then what you should do is just mark and move on. All right, so earlier we talked about what forces act on these two block system. So we would now have to write Newton's law again, saying, okay, the sum of the forces on this system equals the mass of the system times A. And so this would be 2m plus m times A. And we're going to have the 3mg sine theta assisting the acceleration, and the mu k 3mg cosine resisting that motion. So notice the 3m's go away. Okay, and so we're left with A equals g sine theta minus mu k g cosine theta. So this would be point 1, and that didn't take too long, so that's not so bad. Then we think about the fact if we make our VT graph as we do our process here, then this distance d equals the area, and that distance d is 1/2 v final delta t. All right, we don't know v final, so remember that v final equals a delta t plus v initial, and v initial is 0. So I can substitute, and I can say, okay, d is then 1/2 of a delta t squared. And then what we would need to do, well, sorry, making mistakes. Apologize for that. V final is what we're asked for, so I don't want to get rid of that. But we do start with that equation, so pretend I didn't erase that. Right, and so V final is equal to a delta t, and the V initial is 0. So I need to get rid of time. Time is V final over A. So D is 1/2 V final times V final over A. So to find V final then, it's the square root of 2D times A. And then at this point, if I'm short in time, I would just say substitute in A and move on. Try and always save your time. It's the hardest thing about this exam, I would say, is that usually I find my students, and you all might find this too, know their stuff, but just don't have enough time to show it. So the first point is for finding the acceleration. The second is for using a correct kinematics equation. And the third is for a correct answer where you would substitute all of that together. So hopefully that's helpful there. You'll see the alternate solution involves energy, which we haven't gotten to yet, so don't worry about that. Hopefully this was a helpful and informative practice here for doing the 3 questions. Thank you for taking the time to do so. A reminder to do your reflection for your credit, and have a great rest of your day.